All right, let's talk about something that can totally wreck your machine learning model, even if your algorithm is perfect. It's this unsung hero, a step that's so crucial but often gets overlooked. We're talking about feature scaling.
So let's jump right in. Imagine you're starting a new project. You've got all this great data, but there's a hidden trap, a really common one actually. It's this idea of an uneven playing field.
Okay, so picture this. You're trying to predict something and you've got two pieces of information. One is salary, big numbers, hundreds of thousands. And the other is years of experience, maybe a number like 10 or 20. I mean, just look at the difference here. The salary bar is just towering over the experience bar. To us, it's a big difference. To a machine, it's everything.
So what's the big deal? Well, a lot of algorithms work by measuring distances. And when one number is just massive compared to the other, the algorithm basically gets blinded by it. It's going to think salary is way, way more important than experience, not because it actually is, but just because the number is bigger. It's like one feature is shouting and the others can barely whisper. Your model is essentially biased from the get-go.
So, how do we level this playing field? How do we fix this shouting problem? Well, this is where our hero of the day comes in. It's called feature scaling.
And what is it, exactly? Think of it like a great equalizer. It's a process that takes all your different features, with their wildly different ranges, and puts them all on the exact same scale. This way, your model can actually pay attention to what the data is saying, instead of just being influenced by the biggest numbers.
And I gotta stress this isn't just some optional nice-to-have step. For a ton of models, it is absolutely non-negotiable. Getting this right can mean a massive boost in accuracy, faster training times. I mean, it literally makes your whole model more stable and reliable.
Okay, so now that we're sold on why we need to scale, the next question is how? And it's not a one-size-fits-all kind of deal. It's more like a toolkit, you know? You've got different tools for different situations. Let's break down the three big ones you'll run into.
First up, we've got standardization. You might also hear it called z-score scaling. What this does is pretty cool. It basically recenters all of your data so the new average is 0. Then everything is measured by how many standard deviations it is away from that new middle point. So when would you use this? This is your go-to for a lot of classic algorithms. Think support vector machines or logistic regression. It works especially well if your data kind of looks like a bell curve. And a key thing to remember is that it handles outliers pretty well. Not perfectly, but it's not super sensitive to them. All right, tool number 2 in our kit, min-max scaling. People often just call this normalization, and the idea here is super simple, really intuitive. It takes all your data, finds the absolute minimum and maximum values, and then squishes everything to fit neatly into a specific range, usually between 0 and 1.
This is the king when it comes to things like neural networks or when you're working with image pixels. But, and this is a big but, it has a huge weakness. It is extremely sensitive to outliers. Just one crazy, out-of-place number can throw the whole scale off, basically cramming all your normal data points into a tiny little corner. You lose a ton of information that way. So that brings us to our third tool, which is designed to solve that exact problem. It's called the robust scaler. And as the name suggests, it's, well, robust. It's built for messy data that's full of outliers. Instead of using the mean, which gets dragged around by extreme values, it uses the median, the true middle number. It focuses on the bulk of your data and pretty much ignores the crazy stuff on the edges.
This thing is a lifesaver when you're dealing with real-world data, which is almost always messy, right? Think financial data with some massive transactions or sensor data with a few faulty readings. The robust scaler is fantastic because it makes sure those few weird points don't completely warp how your model sees everything else.
So, let's put it all together in a quick cheat sheet. It's pretty straightforward, right? If you've got something that looks like a bell curve, standardization is a great choice. Working with neural nets? Go for min-max. Got a data set with some wild outliers? Robust scaler is your best friend.
Okay, we've got the toolkit. Now let's talk strategy. When do you have to scale? And, maybe just as importantly, when can you actually skip it?
Here's a simple rule of thumb. If your algorithm is based on distance, like k-nearest neighbors, or uses something called gradient descent, like neural networks and regressions, then you have to scale. It's not optional. But for tree-based models, like a decision tree or a random forest, you actually don't need to. Why? Because those models just care about splitting points. They ask simple questions like, is this value bigger than 50? The actual scale doesn't change the yes or no answer to that question.
All right, so we've covered the what, the why, and the how. Now for the really fun part, the real-world impact. And
We also need to talk about the absolute #1 biggest mistake people make, a mistake that can literally ruin all your hard work.
This is it, the big one. The absolute worst thing you can do is scale your entire dataset all at once before you split it into your training and testing sets. This is called data leakage, and it's a huge problem. Think of it this way. You're letting your model learn about the test data during its training phase. It's like giving it the answer key before the exam. You'll get amazing scores, but they'll be completely fake.
So here's the right way to do it, the no cheating method. First, you split your data into a training set and a testing set. Then you take your scaler and you fit it, meaning you learn the scaling rules like the mean or the max value using only the training data. And once you've learned those rules, you apply that exact same transformation to both the training set and the test set. That way, your model's evaluated on data it has truly never seen before.
And when you do it the right way, the results are incredible. Take healthcare, for example. By scaling things like cholesterol, age, and blood sugar, a model can actually give each factor a fair shake. It's not just blinded by the big cholesterol number, it can see the whole picture, leading to way more accurate diagnoses.
Or think about finance. How can you compare a stock that costs $1,000 with one that costs $10? Scaling lets you do just that. It puts them on a level playing field so the model can look at their actual performance and patterns, not just the sticker price. The result? Much better predictions. Same thing in e-commerce. You want to recommend products, right? Well, without scaling, one person buying a $500 TV would look way more important to the model than another person who clicked on 20 different items. Scaling makes sure that all those little signals, the clicks, the time spent on a page, they all get heard. It creates much smarter recommendations. So you see, feature scaling is so much more than just some boring data cleaning step. It really is the unsung hero. It's what allows your models to listen to the real story in the data, not just the loudest numbers. It's the step that transforms a model from something biased and kind of dumb into something genuinely insightful. When you level that playing field, you give yourself a chance to find the hidden patterns, the things you couldn't see before. So the real question is, what will you discover in your data? Thanks for watching.